Good morning, everybody. Welcome to our International Physics webinar. Today it's our 266 International Physics webinar. And we have with us here today Dr. Anthony J. Uh, Cavill Institute of Theoretical Physics, University of California, Santa Barbara, USA. And he has already connected with us. Sir, welcome to our webinar, sir. And thanks for accepting our invitation. So it's a great opportunity for our students and viewers to interact with you. So dear viewers and students, I think you have already come to know the title of this today's International Physics webinar, that is the Quantum Field Theory and Overview. You can also join with us using the link. I'll add the link in the comment section, and you can also ask question by commenting. So sir, it's your time. You can start your session.
Thank you very much
My pleasure,
for
sir.
the invitation to speak about quantum field theory. It's a great pleasure for me to be giving a talk in Bangladesh, and I hope that when this pandemic is over, I will have the opportunity to visit
Yes,
your
definitely.
wonderful.
I'll definitely invite you for a face-to-face session.
Thank you very
Thank
much. So,
you.
thank you. So let us begin. So today's talk is about quantum field theory, and you already have seen this poster. Quantum field theory is arguably the greatest monument to the human intellect. Well, in any case, it's the most accurately tested theory in physics. Now, this is a surprise to some people who feel that perhaps Newtonian physics has been tested more accurately, but that's not true. It's actually quantum field theory. Now, a couple of millennia, it took us a long time before we realized that the universe is pervaded with quantum fields and that we're surrounded by quantum fields. So, what exactly is quantum field theory? Who needs quantum field theory? So, I begin my book with these two questions. Now, who needs quantum field theory? Might be the question that some students might be wondering about. Well, these days, one doesn't even need to know quantum mechanics to be a professor of theoretical physics. I do not speak of experimental physicists for whom I have only admiration since they can do things I cannot even dream of doing. But I mean, you can be a professor of theoretical physics without knowing any quantum mechanics. Uh, so, chapter 1.1 of my textbook on quantum field theory, the very first sentence is who needs it? Who needs quantum field theory? Well, the statement is quantum field theory arose out of our need to describe the ephemeral nature of life. So life is like clouds and smoke passing in front of our eyes, as they say. No, more seriously, quantum field theory is needed when we confront simultaneously the two great physics innovations the last century of the previous millennium, namely special relativity and quantum mechanics. Why is so? Let me explain. So, we can roughly divide physics into four parts. This is what I call the square of physics. Okay, so uh, I don't know if the audience can see the pointer or the.
Yes,
Can you see my pointer on
yes, we
this
can.
axis? Yes, yes. So on this axis, we um, roughly classify things as big things and small things. And on this axis, we talk about roughly classify them as how fast they're moving, whether they're slowly moving or moving very fast. So in this box, we have classical physics, big things moving very slowly, such as ourselves. Okay. Now we all know that when you start talking about fast things, for example, a rocket ship going very fast near the speed of light, uh, then special relativity comes in, but there's no need for quantum mechanics. Now, in the when you have a very small things moving quite slowly, for example, slowly moving electron scattering off a proton, this would be in the hydrogen atom, for example, there is no need for special relativity, but you need quantum mechanics. Okay? So it's in the peculiar confluence of special relativity and quantum mechanics, a new set of phenomena can arise. Namely, particles can be born and particles can die. So a new subject in physics, quantum field theory, is needed to describe birth and death and some kind of life in between. In classical, in the other areas of physics, for example, if you're in atomic physics, there's no such thing as birth and death, right? But when you marry quantum mechanics and special relativity, as in the box up here, when you have small things moving very fast, when you marry the two, quantum mechanics and special relativity, then quantum field theory is needed, a new subject. Okay, so let me explain how that happens. So we have two gold-plated equations of physics. Let's go back to these two almost sacred principles. In quantum mechanics, we have uncertainty principle, which is that the uncertainty in energy is order 1 over the uncertainty in time. In special relativity, the gold-plated equation is that energy could be turned into matter, E equal mc squared. Everybody knows this. So I give below a very rough sort of advertising slogan. If you're advertising these two theories, this first statement is that accounting errors can be tolerated for a very short time. So over a very short time, delta t, okay, energy conservation, because it's uncertain what exactly the value of energy is, that energy conservation could be violated for a very short time. And the second advertising slogan for special relativity is that accounting errors could be turned into stuff. Energy could be turned into matter. Now, these two equations are the sacred two of the gold-plated equations of physics, and each in its domain accounts for many interesting phenomena in quantum mechanics and in special relativity separately. But what happens when they're both of them? Then particles could pop out and pop into the vacuum. Okay, so because you have accounting errors for a very short time, you can have an uncertainty in energy. But if there's no special relativity, then that uncertainty energy would just disappear very quickly. But it's only when you have special relativity that this energy uncertainty could be turned into matter. So particles can appear and be produced. And particles, it could happen in two cases. First, if energy is available, so for example, at a high energy accelerator, or near a black hole horizon, as in Hawking radiation. In contrast, I assume that there are many students in the audience. Many students have taken a course on quantum mechanics, but non-relativistic quantum mechanics, right? Specifically, quantum mechanics without relativity. So in non-relativistic quantum mechanics, it's described by the Schrödinger equation. And you know that no matter what you do to the Schrödinger equation, no matter how you shake and bake the Schrödinger equation, it's always the same number of particles. Suppose you have a Schrödinger equation describing 3 electrons moving around. No matter what you do, there will be 3 electrons, right? The particles cannot disappear or appear. So, but if you have both special relativity and quantum physics, then particles could appear and disappear. So where do we get our notion of a field. So this is based on my book on quantum field theory, and starting with something for the general public. So from mattress to field, imagine a mattress. So mattress, in my in this context, a mattress is just a arrangement of mass points, masses connected by springs, and so it could vibrate. And far away when you're looking very far away on distance scales much larger than the lattice spacing, then this would look like a continuous field. So very far away, this would look like a continuous field, and there could be waves in it, and so on and so forth. And these waves, as you probably know from classical physics, you can form wave packets of these normal modes. And if the spring is not exactly harmonic, if it is harmonic, then the waves would just pass through each other. When it's anharmonic, then these waves would scatter and decay. So that's the basic idea of the connection between fields and particles. So say on the next slide. So when you have a field, you can produce this is a space-time diagram. This is space and this is time. So you can imagine some source here, and you can, in the field, there's a disturbance, and it produces a wave packet that moves to some other place in space and time, and it's absorbed there. Okay, so the field can produce a particle. So that is what the founders of quantum field theory based their physics on. Okay, our fields, you can form wave packets and then particles. Now, this is from a chapter in my book. It's called From Field to Particles to Force. So how do force arise when you have particles? So the force between nucleons comes from the exchange of a pi meson. And so the pi meson can be thought of as a marriage broker in some very old culture, in India, in China, in long time ago, right? That you don't go out dating. It's arranged so the pion can be thought of as a marriage broker. In some Jewish cultures, in many Arabic cultures that still exist. It's typically a rather fat lady, but you can imagine that the lady's, how far she can travel is limited by her weight. I don't know if anybody can read this. Now, this is a cartoon, obviously. So where's it taken from? Well, it's taken from a book of mine called Fearful Symmetry. And here I give you how the force arises. So let me just read this to you, since it's maybe a little bit small, but I don't know if you can read it. Since the early days of physics, the notion of force has been among the most basic and yet the most mysterious. It was therefore with considerable satisfaction that physicists finally understood the origin of force as due to the quantum exchange of a particle. So given this understanding of the nature of force, in 1934, the Japanese physicist Yukawa decided that a marriage broker must be provided for the strong interaction. So boldly, Yukawa hypothesized a new particle, which became known later as the pi meson or the pion, for short. And the most striking thing was that he was able to predict the properties of this particle, the pion, for which he was awarded the Nobel Prize. So this is actually taken from a talk that I gave at the National Center for Performing Arts in Mumbai many years ago. And so I keep showing you this cartoon. So let me remind you that we produce a particle, and from the particle that generates a force. And so this is taken from my popular book, Fearful Symmetry. And here I show you my book, the most recent incarnation of my book. In 1984, so almost 40 years ago, as you know, Steve Weinberg passed away recently. I was sitting in Weinberg's office, and I was thinking about writing a textbook on quantum field theory. So I have indeed written a book on quantum field theory. But his advice in 1984 is that I should write a popular book first. He said many people, many physicists just go ahead and write textbooks, which are impossible to understand because they don't know how to explain things. And if you write a popular book, you have to explain physics to people who don't know anything about physics. So that's the necessary practice before you write a book. So that's how this book, Fearful Symmetry, came about. And the book was, after it was published, it was translated almost immediately into German, Spanish, Chinese, Japanese, and Korean. And then 34 years, it's only 34 years, it took a long time. A French translation finally came out. And this is perhaps a joke about a story about how the French are. It finally came out in 2018 after I lived in Paris for a year. So somehow the fact that I lived in Paris means that they take me seriously and translated the book. And you can see the book here for any of you who reads French. You can see that the title is then translated this. Now I'm hoping that perhaps that after today's talk, there may be a translation in Bengali as well. Now, when I visited Calcutta many years ago, I was told that Bengali is a very beautiful language, and people argue about which is the most beautiful language in the Indian subcontinent, from Pakistan to Bangladesh. And Bengali, I was told, is one of the most beautiful language known to people. There are a lot of poetry and so on. So perhaps there will be a Bengali translation soon. So I show you a French translation. And on the next slide, I show you some Chinese translation. Now here's a very interesting story, because in mainland China, many things were pirated without authorization from the author. So both of these, this book was then pirated, Fearful Symmetry, with the tiger, burning tiger, and they just made up some arbitrary name for me. And this book in China was so successful that they even put out a second edition. So the pirates had put out a second edition, and for the second edition, they even put on the English title, Fearful Symmetry. I show you also the authorized edition, Chinese edition. But, okay. So it's because of this book that I was first invited to visit India. So that's actually the Germans who invited me to come to India. Some of you may have known of this German Indologist, Max Müller. So it was interesting because I was sent, my trip was paid for by the US State Department. And for the purpose of this trip, I was actually considered as a employee or a member of the US State Department, so member of the government, and the consulates had to receive me. And this is what appeared in a Calcutta newspaper, Physicists in Search of God's Plan, and that was almost 40 years ago. The text of my talk in Mumbai was later published in New Literary History, which is amusingly a journal on English literature published in the United States. And for those of you who are interested, you can look for this. So, as I said in the beginning, I've been to Pakistan, And I've been to India. I've been to Pakistan on the invitation of Professor Abdul Salam. And sorry that he has also passed away. Now Weinberg and Salam have both passed away. Glashow is still with us. And someday, perhaps, I would also get to see Bangladesh in person. Okay, so we talked about from field to particles and from particles to force. Another very rough analogy was the following. Going back to the mattress analogy, the mattress which produced the field, you can imagine two lumps on a mattress, and they attract due to the distortion on the field. You can imagine two lumps on a mattress, they compress the mattress, and they that in effect produce an attractive force. Okay, so the physical world then results from a web of interactions, some attractive and some repulsive. Now, when you first started studying physics, right, you know that the professor tells us that the gravitational force is attractive, and the electric force is sometimes attractive, sometimes it's repulsive. If it's between the same charges, then it is repulsive, and if it's between opposite charges, it's attractive. Okay, so this was a complete mystery. The professor just say this. Okay, we just have to accept this. There's no explanation whatsoever. It's very unsatisfying that we're just told that some forces are attractive and some repulsive. And one of the most remarkable things in physics is that quantum field theory now has answered why. Okay, it's able to answer why. The sign of the force between two objects, plus or minus, corresponding to attraction and repulsion, between like objects, I emphasize like, it depends on whether the spin of the mediating particle is odd or even. So, in the analogy that I had before, it depends on whether the marriage broker is spinning, and if the marriage broker is have an integer that has an odd number of units, quantum units of spin, or even units. And ultimately, this sign, whether it's plus or minus, ultimately could be traced to the difference between time and space. Okay? So let's go through the list, how our universe is put together. Spin zero produces an attraction. That was Yukawa's original idea that I mentioned. It's the strong nuclear force. The pi meson has spin zero, and so protons and neutrons are attracted. They come together to form nuclei, and then the world as we know it. The spin one particle, namely the photon, produces electromagnetism and produces a repulsion, and like charges repel. And finally, spin two, namely the graviton, it's an attraction. Okay, it's responsible for gravity. There's an attractive force between the apple and Newton's hand. Okay, so we can now give you a lightning history of the universe. This is the history of the universe in 5 seconds. So the universal gravitational attraction due to the spin 2 particle produces the instability that drives the formation of structure in the early universe. The dense regions becomes denser because gravity always attracts. So some denser region will become even denser because they attract each other, they attract other, and the less dense region becomes less dense. So it's the rich becomes richer, as we all know. So the dense region becomes denser. And in a sense, the photons and the neutrinos, they impose a kind of taxation. They carry energy away because they are free streaming. They move through the entire dense region. So as the region becomes denser and less dense, become denser, it would be a runaway instability, except for the photons and neutrinos. So then you have the attraction between the protons due to the spin zero particle, which ignites the stars eventually and form the rich variety of nuclei. So dense region gets denser and denser, and they form stars. And then the spin zero particles pull the nucleons together to form all these nuclei that we know. And finally, there's attraction between the positively charged nuclei and the negatively charged electrons due to the spin one particle producing the atoms. Okay, that's photon, that's electromagnetic force. So you see how the universe is put together. It's all because of the 0, 1, and 2. So now, where did physicists get this concept of a field? And interestingly, the concept of the field goes back to Faraday. And some of you know that Faraday was born into an extremely poor family. If you have read any of the novels by Dickens, England at that time, Victorian England. And so he was apprenticed as a young boy. And without a proper education, he never received an education. And without a proper education in mathematics, of the continental philosophers were beyond Faraday, who was compelled to invent his own pictorial language. So Faraday tried to, and the mathematics of the continental philosophers nowadays, we would call calculus and differential equations and partial differential equation, what eventually became Maxwell's equation. Well, Faraday was not able to understand any of this. So he invented his own pictorial language, and he introduced the idea of electric and magnetic field. So here, let me make a side remark about basic versus applied research. So at the time of Faraday, the Royal Navy is interested in faster communication in England. So they have to choose between people that are trying to breed stronger pigeons or people that are messing around with wires and frogs. They're these strange physicists. They are sort of in these laboratories, and they have wires, and the frogs trying to produce electricity. And so obviously, we turn out that breeding stronger pigeons is not the way to go. So now we come back to Maxwell's. We'll mention Maxwell's theory. So Maxwell's theory of the electromagnetic field contains two hidden symmetries that will rock 20th century physics, as you probably all know, that namely relativistic and gauge symmetry, ESA. So is it conceivable that present theory also contains a hidden structure? In hindsight, how Maxwell was not able to see that there are these two hidden symmetries is because of the terrible notation of 19th century physics. When I teach electromagnetism, I often ask the student, why is the magnetic field called H? And the electric field is called E. That's obvious because electric starts with E. So why is the magnetic field called H? And none of the students could answer this question because none of these American students have ever read Maxwell's original paper. Well, Maxwell's original paper is, of course, he didn't have vector notation. And so what he did is that the electric field is actually EFG. Okay, the three components have different letters, EFG, and the magnetic field is then HIJ. So it was really terrible notation because you can imagine when you write down Maxwell's equation, what a mess that would be. But nowadays, Yang-Mills theory also has terrible notation. And it's really a redundancy in description. And some of you may have heard about the twistor formalism that burst onto the scene maybe 15 years ago by now. It's perhaps the first step in fixing this, okay? This terrible notation that we have. So already in non-relativistic quantum mechanics, the photon, namely the electromagnetic field of Faraday, was treated as a field, but not the electron. The electron is treated as a point particle. Okay, so in modern, in sort of using American slang, this kind of treatment that you may get in a course of quantum mechanics, it's just half-assed. Okay, it's just very strange. The photon is treated as a field, but the electron is treated as a point particle. So it's this dissatisfaction. It doesn't seem to bother most students. 99% of students don't seem to be bothered. But Jordan, Heisenberg, Dirac was very upset. So they treated the electron, or they proposed the electron should also be treated as a field. So Fermi then came along and made this remarkable statement that if the photons can be created, the electron can also be created. So there should be an electron field that creates electrons. So that was one of the great advances in his theory of weak interaction. So now we have a situation in which all particles are excitation in some field. Each particle is an excitation in some field. The graviton is just a particle like any other, an excitation in the gravitational field. So for example, this is the point of view taken in Weinberg's textbook on gravity. But somehow, the graviton is also responsible for space-time arena in which all fields work and play. So somehow, is the graviton somehow different? So that's, of course, the big question that has bothered physicists for the last 30, 40 years, namely quantum gravity. And where does the cosmological constant come from? We know that now the most likely dark energy is just represented by cosmological constant. So in the beginning of this lecture, I talked about the square of physics, but with gravity, we have to talk about the cube of physics, because then there is another direction, which is the Newton's constant. Okay. So this is the first edition of my book, my textbook on quantum field theory. And as you can see here, it is published in the year 2003. And the favorite paintings by a French painter. And so I picked this painting because of this joke that he's actually painting a student who's trying to reach the green field, the quantum field. But to reach the quantum field here, he first had to get through this whole big mess here, which represents the undergraduate curriculum. Okay, so this is the second edition, the revised edition, what came out 7 years later, 2010. It's now almost 12 years old, and they changed the cover slightly. And then since then, the book has been translated into Russian and into Japanese, as you can see. And the Russian book amuses all my Russian colleagues because on top of here is my name, but the Russian title, since they don't have nuts and nutshells, so they don't have quantum field theory. My book's original title is Quantum Field Theory in a Nutshell, but apparently in Russian that phrase does not exist. And so it's translated into Quantum Field Theory in 2 words. And the Russian physicists were laughing. That's logically inconsistent title. Even the title is more than 2 words. Okay, so now quantum field theory had a very interesting history. I say I've already taken up half an hour. Quantum field theory has had 2 near-death experiences. In the late 1940s, it almost died because it was inability to produce Lorentz covariant results, and then it also contained a lot of divergences. Things were going to infinity and so on. And interestingly, many people, like the older generation, people like Niels Bohr, advocated that quantum field theory be abandoned. And this also included people like Landau. But it's the young people they were the conservatives. Young people were not the revolutionaries. It's the old people that are the revolutionaries. They want to throw quantum field theory away. Or more accurately, say the young people were the revolutionary conservatives. The young people being Feynman, Schwinger, and Tomonaga. So the young people were able to save quantum field theory. Again, in the late 1960s, quantum field theory was also considered dead because it was unable to deal with the strong interaction, which led to the S-matrix school, which was centered in England and also on the West Coast in the United States. So I was very fortunate that I was a student on the East Coast. So many people who study S-matrix theory, they were wiped out. So it turns out that field theory was correct. And one of my professors said the triumph of field theory was like a victory parade that made the spectator gasp with awe and laugh with joy. So now quantum mechanics will understand quantum mechanics is 0 plus 1 dimensional field theory. You can think of it that way. It's quantum field theory in one time and no spatial dimension. And string theory can also be formulated as a 1 plus 1 dimensional field theory. Now let me now step back a little bit, and I will now describe to you what Feynman did. When we teach and when we learn quantum mechanics, it's usually a Schrödinger or the Heisenberg formulas. But conceptually more profound and leading naturally to quantum field theory is the so-called Dirac-Feynman path integral or Schrödinger functional integral formulas. Okay, so let's look at the double slit experiment. So a source emits particles, and the particles go through two slits. There's a screen in the middle. Let's see. Yeah, there's a screen in the middle. There are two holes, two slits, and then the particles then is detected at the point O on a screen. This is the detector. Okay, so we learned in a quantum mechanics in an elementary course that double slit experiment, you add the amplitudes for getting to O coming through this slit or this slit. Okay, now students all nod their heads and so on, and they all write down what the professor said, etc., etc. But students almost never ask, what if there are 3 holes in the screen? Okay. So if there's 3 holes in the screen, well, you just add suppose there's 3 holes, then there's you just add the amplitudes for going through those 3 holes. But what if you add another screen, the student could ask? Well, the professor is getting a little bit impatient, and you obviously then all possibilities have to be considered. The electron goes through this hole and then that hole, and the electron goes through this hole, and you add all the amplitudes. Now finally, the student said, what if you add another screen? And the professor has to say, gets really impatient and says, shut up and be quiet, and I have a lot of material to cover. Now, who was that student? The student was Feynman in my story. Okay, so it's the most zen of all. Suppose we add infinite number of screens and we drill infinite number of holes in each screen. Okay, then we have to add amplitudes over all paths. Okay, so this is the integral over all paths. When you add the amplitudes, Newton and Leibniz told us a sophisticated way of adding is to integrate. Okay, so this is the most zen of all. And quantum field theory could be formulated in terms of path integrals. And human life is, of course, not in the quantum domain, but you can imagine that in the human existence, there are also many, many paths that you can follow. One of the paths is you can study now and party later and enjoy the tenure life. Or you can party, you flunk out, and then you make billions on Wall Street, and so on. Okay, so now I Quantum field theory, as I just explained, is then one big fancy sum. You have to sum over all possible paths, or it's a fancy integral. So we write this integral as integral d phi of some exponential e to the minus s phi. Okay, and phi is a function of x and t, where x is a d-dimensional coordinate, so in d-dimensional space. In quantum mechanics, you just go down one step, but now phi only depends on time. And in fact, we call it the coordinates or the position of the particle. And instead of phi, we call it q. So this is in this sense that I said it's 0 plus 1 dimensional field theory. And then there's a subject in physics called random matrix theory, which I worked on when I was in France, in which phi is then a matrix that it doesn't even depend on time. So it's a 0 plus 0 dimensional field theory. An ordinary integral, then you go down even one more step, is ordinary integral. It's just an integral in which phi is just a number. Okay, so the last 80 years or so of quantum field theory, it's mostly consists of finding methods and tricks to do this integral. So for example, one approach is known as lattice gauge theory, which is to replace the integral by a sum, and then you use the computer. Okay, so now I can teach you what a Feynman diagram is. When I was a student, I was really eager to learn about Feynman diagrams, which I heard so much about. So I really wanted to learn what Feynman diagrams are all about. Well, Feynman diagram is the simplest explanation of Feynman diagram that I know of is this. Suppose I ask you to do this integral, okay? This integral cannot be done analytically if g is not 0. But I could expand the e to the minus g phi 4 in an infinite series. I can expand the exponential. And then each one of these integrals is a Gaussian integral, which I can do, which any student could do. So then Feynman had this fabulous idea, which is draw little diagrams to keep track of all the different terms, the infinite number of terms. You just draw diagrams to keep track of all these terms. And that's basically Feynman diagram, but in the context of the path integral for a quantum field. And on the next slide, I show you Feynman's last blackboard. And when he died, I invite you to look at these two boxes up here. I don't know if you can see. He sets impossible standards for himself, the two upper box. The top box is that what I cannot create, I do not understand. And the second thing is know how to solve every problem that has been solved. Now, I don't know if students in Bangladesh could set this as a standard, but as far as I'm concerned, it's an impossible standard. I certainly do not know how to solve every problem that has been solved, but that's what he's written on his blackboard. But notice this very interesting thing. He says here, and there's another box, to learn. And these are the things he wanted to learn. And notice the interesting thing is that the Kondo problem has been crossed out. He felt that he's fine, must have figured that has learned the Kondo problem. So you see there's still many things Feynman wanted to learn. He wanted to learn how to do the Weber-Ansatz problems, and so on. Okay. So Schwinger and Feynman had a race in 1948, but Schwinger was able to beat Feynman. And Schwinger in 1948, he calculated the first term of the anomalous magnetic moment of the electron. And it's called anomalous because it's the deviation from Dirac's value. Dirac had a very famous prediction, and he calculated the deviation from Dirac. And this expression, the formula, the expression of his quantum field theory result is carved on his tombstone. And Feynman admitted that he lost. Okay. So the current value for the anomalous magnetic moment of the muon is 116,587,705.7, and the error is 2.9 times 10 to the minus 11. And Schwinger got the 116. So this is what Schwinger's calculation is, the 116. Okay. Then later, other people calculated these figures. So this is why I said quantum field theory is the most accurately tested theory in physics. The agreement between theory and experiment is astounding. It's amazing. Now, to put the accuracy in rough pictorial perspective, probably many of you could visualize in your mind the travel distance, which I looked up on the map between Pabna and Dhaka, and it requires going by car and by ferry. The total distance given on Google is 154 kilometers. Then the present uncertainty, this uncertainty between theory and experiment, corresponds approximately to 0.006 millimeter. Okay, and for comparison, the width of a human hair ranges from 0.017 to 0.18 millimeter, depending on how thin and how thick your hair is. Okay, so you just think about the distance between Pabna and Dhaka, and then that what quantum field theorists, the measurement, the prediction of this distance, the experimental, the disagreement between theory and experiment is now smaller than that of a human hair. Okay. In fact, you can see it could be, if you take this as the standard, 30 times smaller. Okay, so as I said, Schwinger calculated that Schwinger had a great triumph, and this is taken from my quantum field theory book. So in modern day language, Schwinger, of course, did not use Feynman diagrams. Feynman was invented this. Schwinger did not use any diagrams at all. And there are these diagrams these are all the relevant diagrams. This is the one that Dirac has calculated, and Schwinger calculated this one. Okay. So Schwinger is very upset, and he said that Feynman has brought quantum field theory to the masses. So, in fact, when I was a student at Harvard, when Schwinger was there, Feynman diagrams was not allowed. And this is what Paul Martin said, that in the dark recesses of the sub-basement of Lyman, Lyman is the building for the Harvard Physics Department. It's a very old building. And you go down not only to the basement, but the sub-basement, where the theoretical students retire to decipher the tablets and where the ritual taboo on pagan pictures could be safely ignored. Okay, so students that want to draw Feynman diagrams have to go down to the sub-basement, and they were told that Schwinger never goes down there. They secretly work things out using Feynman diagrams and then show the results to Schwinger without the Feynman diagrams. Well, as you all know, Schwinger and Feynman got the Nobel Prize together, and and this is a photograph from of the two of them at the Nobel ceremonies. And what is really amusing to me is that they have such different personalities. And you see that Feynman is talking and joking, and Schwinger, you can see his just his body language. He still is on one hand still has his white gloves, and you can see his body language. He said he tried to get away from this guy as much as he can. And Stanley Desser, who was a student of Schwinger's, and he has written recently. Stanley is now more than 90 years old. He's one of the great men of that generation. He knew both of them, and the most remarkable thing is that remarkably, they have their backgrounds almost the same. They have the same background. They're both middle-class Jewish Americans from New York City, but their personality is completely different. So there are several landmarks after that. After Feynman and Schwinger, there are several landmarks in quantum field theory. Obviously, I cannot go into any detail. The landmark is first Heisenberg with his invention of isospin, the discovery of internal space. The second is that of gauge symmetry, discovery of gauge symmetry by Hermann Weyl, and finally non-abelian gauge theory of Yang and Mills. So there's a simple introduction for undergraduates who want to learn a little bit of quantum field theory in part 9. I published this book with Princeton University Press in October 2020, 2 years ago, called Fly-by-Night Physics. And for those undergraduates who are interested in quantum field, you can read a little bit of that book. So the influence of Feynman diagrams on quantum field theory was total, absolute for many, many years. And even when I was in graduate school, I'm old enough to be in graduate school, that I was told by a drink of water. Get a drink of water. I was told by one professor that quantum field theory is just the sum of Feynman diagrams. So this was the attitude for a long time. And one of the most exciting developments occurred in the mid-1970s, which I call breaking the shackles of Feynman diagrams. And by two young guys, one in the Netherlands, one in Russia, Torov and Polyakov, and many others, they discover non-perturbative structures, things that go like e to the minus 1 over g squared, which you obviously cannot see by expanding in g squared. There are all kinds of features that cannot be seen by duality, topology, and all kinds of exciting new stuff. So I've written a popular book on quantum field theory to be published by Princeton University Press around June. This is wrong, around June 2022, this year. Sorry, this is wrong. I'm too optimistic. It's a popular book based in part on this lecture because some people, Princeton University Press, have heard about this lecture, and in fact, it's at a somewhat lower level. So quantum field theory. So finally, I'm come to near the end of my talk, and I want to ask of studying physics. So if you ask some American physics students, somebody might answer that the purpose of studying physics is to make a lot of money. That's the wrong answer. So what is the purpose of studying physics? Well, the purpose of physics is to understand nature. We want to understand as much of nature as possible. And let me give you an example, what I call intellectual completeness of different area of physics. So the example is that, for example, Pauli exclusion principle, the spin statistics connection, you know that particles with integer spin are called bosons. They're named after the Indian physicist Bose. And half integer spins particles are called fermions, named for Fermi. And there's a book by Duck and Sudarshan. I think Sudarshan is an Indian-American physicist from India originally, in which they say there is no one fact in the physical world which has a greater impact on the way things are. Okay, so you probably all learned the Pauli exclusion principle and the spin statistics connection in a course on undergraduate quantum mechanics. So from atoms to neutron stars to lasers, much of condensed matter physics, for example, band structure, superconductivity, etc., it's all based on this connection, this fact. But it's just a rule in non-relativistic quantum mechanics. If you take a course on non-relativistic quantum mechanics and you ask Pauli exclusion principle, the professor cannot answer. Professor quantum mechanics cannot answer this. So quantum field theory is more complete than quantum mechanics because it turned out that in quantum field theory, the Pauli exclusion principle can be derived. And in fact, a stronger version called the spin statistics theorem can be derived. So if you want to understand the Pauli exclusion principle, you have to go to quantum field theory. How do you know that all the electrons are identical in the universe? Right? So many physicists take this for granted. If I go around and ask you, how do you know that the electrons are identical? They could have been made in a factory somewhere. And factory cannot be perfect. Some of them are slightly different from the others. So we need quantum field theory to explain this fact that all the electrons are identical. And the explanation is so elegant and so simple that it has to be correct. Quantum field theory produces an elegantly simple explanation because it says all the electrons are just excitations in the electron field. The electron field is like, you can think of it like a mattress at the beginning of this lecture. And it's just, the electrons are just wave packets in this electron field. Another question you can ask is, why is the electron charge exactly equal in magnitude to the proton charge? Again, when I study physics, the professor says, well, the electron has charge -1 and the proton is charge +1, and they're exactly equal. And this exact equality has been measured to tremendous accuracy. And the reason is that if this charge is slightly different, then the universe would have an excess of one charge over the other. And since electrostatic force is so much stronger than gravitational force, this equality must hold to extremely high accuracy. In that sense, quantum electrodynamics is intellectually less complete than gradient phi theory. It turns out gradient phi theory can explain why these two charges are exactly equal, but not quantum electrodynamics. So if you ask Feynman this question, he has no answer until quantum gradient phi theory came along. So another question is, why is space-time 3 + 1 dimensional? And quantum field theory can be written in any space-time dimension. You can write it in any dimension you want. It can be written in 7 + 1 dimension, or 1 + 1 dimension, or 2 + 1 dimension. So in that sense, it's less intellectually complete than string theory. Now, string theory can predict the dimension of space-time, although the prediction is slightly off. As you probably all know, string theory can only work in a space-time that is 9 + 1 dimensional. And so they have to compactify 6 of the dimensions. So we don't know the answer yet to that question. And finally, one of the deepest mysteries of physics is that the dynamical evolution in the quantum world, e to the -iht over h bar, and the Boltzmann factor in statistical with finite temperature, they have very much the same form. So imaginary time and inverse temperature are somehow connected. So some people, physicists, seem to be split into two groups, two camps. Some people think this is just a coincidence, and some people think there's some deeper meaning to this. I don't know. I really don't know. Sometimes I think it's just a coincidence. But in any case, it can be applied. So for example, the Hawking temperature of a black hole can be applied by going to imaginary time. And imaginary time corresponds to temperature. And so this is also discussed in my quantum field theory book. So once again, quantum field theory can be used because the partition function cannot be represented as a Euclidean field theory in contrast to Minkowskian field theory, because it's imaginary time, and so it's the space-time is then Euclidean instead of Minkowskian, because time is now also the same signature as space. So many other problems in physics can be represented as field theories. And so I come to the end of my talk. In conclusion, there are two great marriages in physics. In 20th century, the great marriage is between quantum physics and special relativity. And when these two subjects are married, we get quantum field theory. So that battle, that marriage is now being established. And late 20th century, which is lasting until early 21st century, and the problem is still not solved, which is that how do you combine quantum physics with general relativity? So I'd like to say that Einstein has two daughters, special and general relativity. And whether that leads to string theory or something else, we don't know. So to the extent that general relativity contains special relativity, string theory also contains quantum field theory. Okay, so this lecture is supposed to be for 1 hour, and I see that I finished it a few minutes early. Thank you very much. Thank you.
Yeah, thank you, sir, for your wonderful presentation, sir. So the video will remain in Facebook and YouTube. We haven't found any question. I think you have explained it very well. So if I'll get any question later, I'll communicate with you. And thanks again. So
okay,
hopefully in the near future we'll invite you for a face-to-face session, and I will very happy to do that. So thanks again, sir. Have a nice day.
Thank you. Okay, thank you very much.
Bye.